Now we're going to discuss the graphs of equations in two variables. Typically, the two variables will be x and y. Not only how we can graph those, but also how we can find the intercepts and whether we can dictate whether there is any symmetry in the graph. The first way we're going to learn how to graph is the simplest, most elementary way of graphing, which is by plotting points. This is the simple table method, where your x can be any number you choose. Generally, the first place you would start is around 0, and we test any x's around 0. So we test x is 0, x is 1, x is 2. But also we test rather than x is -1 or if x is -2. And we try to test all of those numbers in and around the origin and see what's happening and what we get for y. So we take those x's and we plug them in to what the graph is. The graph was given to us. So if the graph is y equals 3 minus x squared, we're going to plug this x in for the x of the equation. So that means y is going to be 3 minus -2 squared. Well, that's 3 minus -2 squared is -2 times -2, so that gives me 4. And 3 minus 4 is -1. So since this is x and this is y, I'm going to have a point on my graph at -2, -1. And we're going to do this many more times, as many times as it will take you, so you can understand what the graph is doing. Sometimes it only takes 3 points, sometimes you need 5 or 7 or 9 points, so you can see how these all connect together. You want a very clear vision so you can get the picture right. So now we're going to plug in a different x. This time we'll try x is -1. So we plug -1 into the original equation. So we plug -1 in for x, and we get 3 minus +1, which is 2. So I'm going to have a point located at -1, 2. So both of these points will be on my graph. Both of these points will also be what are called solutions to the equation. Any points on the graph are also solutions to the original equation. Let's try 0. 3 minus 0 squared is 3 minus 0, which is 3. So I have a point at 0, 3. You can see that this is starting to make a bend. Let's see what happens on the other side. When I plug 1 in for x, I get 3 minus 1, which is 2. So I'll have a point at 1, 2. Let's try x is 2. And we'll have a point at 3 minus 4, which is -1. So 2, -1 will be another point. So at this point, I think it's pretty clear that this is going to be what we're going to call a parabola, and it is going to be upside down. A parabola is nothing more than a U, which goes forever and ever in both directions. If you weren't clear at this point, you certainly could pick another point, maybe try 3 this time, and find out where its next point would be. And then you could find -3 and find out where its next point is going to be, and then you could try connecting those together. So the table method is going to be your easiest, most visual way of creating a graph. If you have a graphing calculator, they do become quite handy. However, some classes don't allow graphing calculators in the classroom, but it's also just a nice tool just to make sure you're doing it correctly so you can check your homework as you're moving through it. But be aware that this might not be able to be used on your exams. So be very careful that you're practicing also with a regular scientific calculator. But you can always put these graphs in by going to your y equals screen. When you put that graph into your y equals screen, you've got 3 minus x squared. And when we graph it, you can see that the graph looks very similar to the graph that we have over here. So it's a good way of checking your answer. One thing I'd like to mention is when I said earlier that any point on the graph is also a solution, you can see that I have labeled and determined 5 points so far. But do note there are many, many more than just 5 points on this graph. In fact, there's infinite number of points in between the points that I have labeled. All of these points, infinite number of them, are also points on the graph, which are also solutions on the graph. So there's actually infinite number of solutions to this graph, which means there's infinite number of points. Sometimes points are not on the graph. For example, a point out here is obviously not a point on the graph, therefore it will not be a solution. So what I'd like you to do is check these 2 points and see if either of these 2 points are on this new graph. Instead of having the graph to determine that, we can simply type these coordinates into our equation to find out. So we're going to rewrite this equation, but we're going to plug in for y, we're going to plug in 0, and in for x, we're going to plug in -2. So this becomes 0 equals -2 to the third minus 2 times -2 plus 3. So when we add all this together, -2 to the third power is -8. -2 times -2 is +4. And when I add all of that together, you get -1. And you could see that 0 is definitely not equal to -1. So that means this point is not on the graph. So let's try another one. This time we'll try 2, 7. So again, we plug 7 in for y, and we plug 2 in for x. And we see whether those 2 sides are equal. Well, on the right-hand side, I have 2 to the third, which is 8, minus 4, plus 3. And you see 8 minus 4 is 4, plus 3 is 7. And if we compare the left side with the right side, you can see that definitely those 2 sides are equal. So that means 2, 7 is on the graph. Now to find the intercepts are going to be the points of the graph that intersect the axes. So if we look back up to this graph again, the y-intercept will be this point right here. This point is what we call the y-intercept. It only has one. It is the only place where the graph crosses this y-axis. Now the x-intercepts are anywhere where the graph crosses the x-axis. And you can see that it's crossing in 2 locations. So both this point and this point are what we're going to call the x-intercepts. So we have 2 x-intercepts, but only 1 y-intercept. You can have many x-intercepts. If this was a sinusoidal function, it would go up and down infinitely forever. And you could see that that would have infinite number of x-intercepts. So there might be more than just 1 or 2. In order to find the intercepts of the graph, what we're going to do is we're going to first write the definitions. So the x-intercept is the point or points where the graph crosses the x-axis. The y-intercept will be the point or multiple points where the graph crosses the y-axis. So to find the intercepts on this particular graph down here, you're going to see that the x-intercepts are going to be located here and here. The coordinates of those points is going to be 5, 0, and negative 5, 0. The y-intercepts are going to be here and here. Those points are located at 0, 5, and at 0, negative 5. At this point, I'd like you to notice where the zeros are in those coordinates. The zeros are specifically located in the spot that will help us in determining in the future where to find those intercepts. So for example, the X-intercepts will always have a 0 in the Y position. Y-intercepts will always have a 0 in the X position. And that will always be true. So let's dig in a little deeper with intercepts. To find the intercepts from this particular equation, to find the X-intercept, which would be this point right here, let's say this point is A, 0. And if I wanted to find that X-intercept, I'm looking for A, 0. So what we're always going to do is we're always going to set the Y equal to 0. To find the Y-intercept up here, let's say this is B high, the coordinates of this point are going to be at 0, B. Notice that we always set the X coordinate right here equal to 0. So to find the intercepts of a general equation, you're going to find the X-intercept by substituting Y equals 0 into the original equation. So up here, we're going to set Y equal to 0. So that gives me 0 minus 14 equals 7x, and then we solve this for x. So we have negative 14 equals 7x, and when I divide both sides by 7, you get x is negative 2. So that means my y-intercept is going to be located at x is negative 2 and y is 0. So that's going to be my x-intercept. To find the y-intercept, we'll reverse the process. To find the y-intercept, we set the opposite letter x equal to 0. So up here in the original, we're going to set x equal to 0. That gives me y minus 14 equals 7 times 0. So y minus 14 equals 0, and when I add both sides to 14, I get y equals 14. So that means the coordinates of my y-intercept says x is 0 and y is 14. So on a graph, a real small sketch of a graph, I would have an x-intercept at negative 2, 0, and a y-intercept at 0, 14. Which is way up here. Now I don't know exactly what it's doing in between there. We will learn tips on how to connect the dots a little bit easier by learning trends that exist with certain equations. For now, we're only looking for those two intercept points. It very well could be just a straight line through. Let's try another. In part B, let's do the same thing by finding the x-intercept. And remember, to find the x-intercept, set the opposite letter equal to 0. So I'm going to put y as 0 in there. So that gives me 0 equals negative x squared plus 4. I'm going to add x squared to both sides. So that gives me x squared equals 4. And by utilizing the square root method that we learned, that's going to give me x equals plus or minus 2. So it looks like I'm going to have 2 x-intercepts. The first x-intercept will be at 2, 0 for y. The other one will be at -2 for x and 0 for y. So I have 2 x-intercepts. And again, that's totally possible. If you recall back to the first question we did, this question at the very beginning also had 2 x-intercepts. So it's very possible to have 2. So now let's look at the y-intercepts. The y-intercepts, remember we set the opposite letter equal to 0. So we're going to put x is 0. So we'll have y equals -0 squared plus 4. Well, 0 squared plus 4 is simply just 4, so I already have my y-intercept. 0 for x, 4 for y. So I know as a little small mini sketch of this is going to look like x-intercepts at 2, 0 and -2, 0, and a y-intercept at 0, 4. So this very well could be an upside down parabola. I'm not sure. Again, we'll learn tips on how to connect those together, but for now I do know those intercepts. The intercepts are probably the most integral part of a graph. Now we're going to learn how to test an equation for symmetry with respect to the x-axis, the y-axis, and the origin. A graph will be symmetric to the x-axis if for every point on the graph there exists another point x, -y, also on the graph. So let's look at an example of what that means. So for example, if I have this point right here, we'll call this x, y. A point that will be symmetric about the x-axis means the exact same point will be on this side of the x-axis, meaning it will be the exact same distance away from the x-axis, like a mirror image of each other. And then the coordinates of this point will be the same in the x direction, but instead of being a positive y, it's going to be a negative y. So this general rule of thumb says that for every positive y, xy on the graph, there will be an x negative y on the graph, meaning the same point below the x-axis. So these 2 points are symmetrical of the x-axis from each other. This graph might be a sideward pointing parabola. That's just one of many options that it might be. The part of the graph that is above the x-axis is a reflection of everything below it. So that means everything in blue up here will be an exact mirror image of everything in red below it. So in other words, if I were to fold this paper in half, everything up here is an exact replica of everything down below. So what point on the graph that's symmetric with respect to the x-axis of the graph would be the point -3, -4? Well, if we use just the formula up here, all we have to do is leave the x alone. You'll see the x coordinates with the x, but the y will change from its sign to its opposite sign. So that's what we're going to do with the point -3, -4. We're going to leave x as is, but we're going to change y to its opposite sign, so it becomes a +4. And again, a quick little sketch is always really nice to be able to determine whether you put it right. -3, -4 is a point down here in the third quadrant. The new point that I'm suggesting is symmetric to the x-axis is -3, +4, which would be this point up here. And I can see that those points do look to be the same distance away from the x-axis, so I feel confident that that is indeed the answer. Another type of symmetry is the y-axis symmetry. The y-axis symmetry acts very similarly to the x-axis symmetry. However, it will be symmetric over the y-axis instead. So for example, any point on the y-axis, or would be symmetric to the y-axis, will have the same point on the other side. So if I have a point over here, well, let's call this point right here, x, y. It will have another point on this side, directly same distance away from the y-axis, in the opposite direction, horizontally across, and it will be at the point negative x, y. For example, this graph might look something like this, where these points are symmetric about each other, and everything on the left-hand side of the y-axis in blue, everything over here, would be an exact mirror image of everything on the right-hand side, which would be in red. And these are mirror images of each other. So for every point xy on the graph, there will be a point negative xy also on the graph. The part of the graph to the right of the y-axis is a reflection of everything on the left. So for example, if I had the point negative 2, 3, a point that would be symmetric to the y-axis, all you have to do is change the sign of the x coordinate, and you leave the y coordinate alone. So we'll leave the y coordinate alone and change the sign of the x. And again, a tiny little sketch always helps to prove this. If I have the point negative 2, 3, a point symmetric to the y-axis would be 2, positive 3. So you can see that these 2 points are symmetric to each other on both sides of the y-axis. Now the last type of symmetry is symmetry with respect to the origin. Origin symmetry means that for every point xy in the graph, not only does the x also become negative, but the y does as well. So for example, if I have the graph like this, for every point xy on the graph, there will be a point negative x, negative y. See how this point x is x distance away? Well, this point x is negative x distance away. This point is y above the x-axis. Well, this point is y below the x-axis. So you can see that this has symmetry about the origin. Another thing that you'll notice is it tends to just be a 180-degree spin. So anything that's in this quadrant up here, if we rotated that 180 degrees around the origin, it's going to end up down here in the third quadrant. Same thing for fourth quadrant. Anything here will be a mirror image of a 180-degree flip around, and it would be here in the second quadrant. So you could see that this just took a rotation and is now down in the third quadrant. That's also how you can notice whether that is origin symmetry. So what point then would be on the graph that's symmetric with respect to the origin of the point 1, 4? Remember, x becomes opposite, y becomes opposite. So negative 1, negative 4 would be a point that is symmetric to the origin. So let's look here. 1, 4, and negative 1, negative 4. So if I took this point and I rotated it from the first quadrant, and I rotated it all the way down here to the third quadrant, you could see that that definitely has an origin symmetry. Or you could look at it this way. Anything in this quadrant is going to have an x or a y-axis reflection, and then an x-axis reflection. So it reflects y and x at the same time.